proposed in space propulsion technologies describe the propulsion technologies that could meet future space science and exploration needs. These propulsion technologies are intended to provide effective exploration of our solar system, and will permit mission designers to plan missions to fly anytime, anywhere, and complete a host of science objectives at the destinations, and with greater reliability and safety. With a wide range of possible missions and candidate propulsion technologies, the question of which technologies are best for future missions is a difficult one. A portfolio of propulsion technologies should be developed to provide optimum solutions for a diverse set of missions and destinations. In-space propulsion begins where the upper stage of the launch vehicle leaves off performing the functions of primary propulsion, reaction control, station keeping, precision pointing, and orbital maneuvering. The main engines used in space provide the primary propulsive force for orbit transfer, planetary trajectories, and extraplanetary landing and ascent. The reaction control and orbital maneuvering systems provide the propulsive force for orbit maintenance, position control, station keeping, and spacecraft attitude control. Current technology. A large fraction of the rocket engines in use today are chemical rockets. That is, they obtain the energy needed to generate thrust by chemical reactions to create a hot gas that is expanded to produce thrust. A significant limitation of chemical propulsion is that it has a relatively low specific impulse, ISP, which is the ratio of the thrust produced to the mass of propellant needed at a certain rate of flow. A significant improvement, above 30%, in specific impulse can be obtained by using cryogenic propellants, such as liquid oxygen and liquid hydrogen. For example, historically, these propellants have not been applied beyond upper stages. Furthermore, numerous concepts for advanced propulsion technologies, such as electric propulsion, are commonly used for station keeping on commercial communications satellites and for prime propulsion on some scientific space missions because they have significantly higher values of specific impulse. However, they generally have very small values of thrust and therefore must be operated for long durations to provide the total impulse required by a mission. Several of these technologies offer performance that is significantly better than that achievable with chemical propulsion. Metrics. In-space propulsion represents technologies that can significantly improve a number of critical aspects of the mission. Space exploration is about getting somewhere safely, mission enabling, getting there quickly, reduced transit times, getting a lot of mass there, increased payload mass, and getting there cheaply, lower cost. The simple act of getting there requires the employment of an in-space propulsion system, and the other metrics are modifiers to this fundamental action. Development of technologies will result in technical solutions that improve thrust levels, ISP, power, specific mass, or specific power, volume, system mass, system complexity, operational complexity, commonality with other spacecraft systems, manufacturability, durability, and cost. These types of improvements will yield decreased transit times, increased payload mass, safer spacecraft, and decreased costs. In some instances, development of technologies within this TAR will result in mission-enabling breakthroughs that will revolutionize space exploration. There is no single propulsion technology that will benefit all missions or mission types. The requirements for in-space propulsion vary widely due according to their intended application. The described technologies should support everything from small satellites and robotic deep space exploration to space stations and human missions to Mars applications. Technology area breakdown. The technology areas are divided into 4 basic groups. 1. Chemical propulsion. 2. Non-chemical propulsion. 3. Advanced propulsion technologies. And 4. Supporting technologies. Based on the physics of the propulsion system and how it derives thrust as well as its technical maturity. Additionally, there may be credible, meritorious in space propulsion concepts not foreseen or reviewed at the time of publication, and which may be shown to be beneficial to future mission applications. Defining technologies. Furthermore, the term mission pull defines a technology or a performance characteristic necessary to meet a planned NASA mission requirement. Any other relationship between the technology and a mission, an alternate propulsion system, for example, is categorized as technology push. Quote, also, a space demonstration refers to the spaceflight of a scaled version of a particular technology or of a critical technology subsystem. On the other hand, a space validation would serve as a qualification flight for future mission implementation. A successful validation flight would not require any additional space testing of a particular technology before it can be adopted for a science or exploration mission. The challenge, for both human and robotic exploration, traversing the solar system is a struggle against time and distance. The most distant planets are 4.5 to 6 billion kilometers from the Sun, and to reach them in any reasonable time requires much more capable propulsion systems than conventional chemical rockets. Rapid inner solar system missions with flexible launch dates are difficult, requiring propulsion systems that are beyond today's current state-of-the-art. The logistics, and therefore the total system mass required to support sustained human exploration beyond Earth to destinations such as the Moon, Mars and near-Earth objects, are daunting unless more efficient in-space propulsion technologies are developed and fielded. Primary propulsion technologies. Work being performed at the Glenn Research Center develops primary propulsion technologies that can benefit near and mid-term science missions by reducing cost, mass and/or travel times. The in-space program is working to develop next-generation electric propulsion technologies, including ion and Hall thrusters. Solar sails, which are a form of propellantless propulsion, are also being developed. Solar sails rely on the naturally occurring sunlight for the propulsion energy. Other propulsion technologies being developed include advanced chemical propulsion and aerocapture. See also. Further reading. Fullerton, Richard K. Advanced EVA Roadmaps and Requirements. Proceedings of the 31st International Conference on Environmental Systems. 2001.